Hi everybody, and welcome to my presentation about Trinity, a PSP emulator escape. I'm so happy and excited to be on stage today and talk in front of such an amazing audience. So, my name is Nguyen, the hardest last name in the world. And a fun fact about me is that I'm a Google engineer at a Microsoft conference talking about the product by Sony. But this is all private research and is not affiliated or associated with the companies above in any way. So what's the product? It's the PlayStation Vita, which is the successor to the PlayStation Portable, and it was released in 2012. To me, in my opinion, it's twice as good as the PSP. It has got double the resolution, it has 2 analog sticks, it has a touch screen and a touchpad on the back, and it runs with 444 megahertz and is capable of running HD games. Unfortunately, it wasn't so successful, and I looked up the sales information. The PS Vita sold 10 million of units, whereas the PSP sold 70 million of units. And in comparison, the Nintendo Switch sold 50 million. But the homebrew scene is great. Even though Sony let the console die, we, the homebrew scene, decided to revive it, and we wrote a lot of homebrew games, applications, emulators, and plugins to overclock the device or increase the resolution in games. And it was all possible thanks to a jailbreak release in 2016 by T-Molecule. Now, what about the hardware architecture? The relevant part for us is it runs on an ARM Cortex-A9 processor, which is 32-bit. It also has a trust zone implemented, and there's a mixed processor integrated for PlayStation Portable game support. Now, the interesting part. What about its security? Considering that this device is almost 10 years old, it's amazing how many security mitigations there are. They have implemented address-based layout randomization and execute never bit in userland and kernel. And basically that means that to exploit a memory corruption bug, you also need an information leak. And as a consequence of XN, you cannot execute your shell code in some data segment, but you need to use the rob chain. There's a domain access control register, which is similar technology to SMAP and SMAP, and prevents you from accessing user memory or executing user code in kernel. They have also implemented stack protection in userland and kernel, and the stack cookie is not a constant. And they have implemented sandboxing and syscore randomization, where the main restriction is that you're only allowed to invoke syscalls from the current process. In theory, you may be able to invoke other syscalls if you only have a reference. And that's exactly what syscore randomization is trying to prevent. They have also applied coarse-grained locking, which is bad for performance, but it does avoid race conditions. Not sure if that is intended or developers were just lazy. And to prevent stupid mistakes, they have removed all unsafe libc functions from the operating system, such as string copy, string printf, and there's no cheat, which is not really a security mitigation, but it makes it harder to exploit something because you need to write rob chains. So, what are the attack vectors? Usual attack vectors for gaming consoles are file format, like libtiff corruptions or so, which were used on the PSP. But on the PS Vita, it's difficult to pull them off due to ASLR. The PS Vita, so another possibility is to abuse save games. And interestingly, it's possible because old games were compiled without PI and without stack protection. So you can easily find buffer overflows and smash the stack. PS Vita has got a dev kit, has got an internet browser which uses a WebKit. And given the amount of public vulnerabilities, it's quite easy to exploit it. And it's also the best entry point because it offers the end user the easiest installation. But it is heavily sandboxed, and has only low privileges, even lower than safe games. And a remote attack may be possible. So differently from file formats, you usually send some message and expect some response. And if there's some bug in the response, you can leak some information and use that to further exploit it. And that's a challenge for me. And an exotic attack surface is the PSP emulator. It's especially interesting because it runs with system privileges, which are equivalent to root. And also, we can use the MIPS processor for doing logic. Now, first a bit about the PSP emulator internals. So as mentioned before, there's a MIPS processor integrated. And so other things which are emulated is audio, memory stick, or the media engine, network, or the controller. And because the MIPS processor has not access to these hardware devices, it has to communicate with the ARM processor over RPC. And for that, it uses a shared SRAM and also a shared CD-RAM, where it's only a subset of the RAM. So basically, if you have code execution in the ARM processor, you can easily manipulate the memory and get code execution in the MIPS processor. But vice versa is more difficult, and that's the task of today. So the plan of attack is to start in MIPS userland and somehow find holes in the RPC server and attack it. But for that, we need the ability to send arbitrary RPC commands. And for that, we require MIPS privileges, MIPS kernel privileges. And assume we were able to break out of the emulator, the last goal would be to escalate privileges to ARM kernel. All right, let's get started. So the security mitigations that I have described before apply to the ARM processor and the Vita firmware. But the MIPS processor and the PSP firmware is less secure. And it's no surprise because it's almost 15 years old. Previous hacks usually exploited out-of-bounds writes to knob out instructions. And the strategy is to find indirect jumps in syscall, which use registers that come from userland, and then knob out instructions such that your argument would be picked instead. The PS3 also had a PSP emulator. However, it's all done on high level. And especially the crypto engine is emulated, which contains private keys. And unfortunately, the PS3 got hacked by GeoHat, and people were able to derive these keys to sign executables on the PSP. And the same thing can be used for the PS Vita. So that means that MIPS user code execution is for free. And we can already checkmark it. The next step is to hack the MIPS kernel. So there's an important data structure in kernel which is used for resource tracking using UIDs. And each UID points to a control block which contains information of the resource. And every control block is structured in a tree hierarchy. The problem is the UID is not random. It doesn't really need to be random, but the design is it's calculated from the control block address. So, for example, if you open a file, such a UID is returned, and when you operate on the file, you pass the UID to kernel, and the inverted equation is used to calculate the control block address from the UID. And the design flow is you can pass any UID. So the kernel will just dereference an untrusted pointer. So the way we attack is similar to a heap unlink, which you may be familiar with, like linked list exploitation. So we plant a fake control block in kernel, encoded as a string, and then calculate its UID. And the control block contains a function pointer as parent and a user address as next child. Then we delete the UID and overwrite the kernel function pointer with that address. And finally, we can just invoke it and enjoy kernel mode execution. However, this vulnerability was mitigated with an integrity check, namely by storing the UID itself in control block and XORing it with a random seed, which is globally initialized. So if we find out that seed, we can craft our control block and then do the exploit. The second vulnerability is in this syscall here, where parameters come from userland and pointers point to user memory. That's a side effect of not having supervisor mode access prevention. The syscall is simple. It returns an error code if the index is too large, and it returns 5 if the index is 0, where 5 is the value of the global array. Now the bug is, in points to user memory, and it's fetched twice, and there's no locking involved. So that means that there's a small window where the value of in1 can change. And it's a so-called time of check to time of use bug. And that's how we exploit it. We spawn 2 threads, where the first executes the syscall, and the second interchangeably swaps the value of in1 between 1 and 1 that is out of bounds. If the error code, if the result is the error code, it means that we swapped too early. If the result is 5, it means that we swapped too late. And if it's something in between, it means that we were able to swap just in that tiny window, and the result is the value we want. Now we do the procedure in 2 rounds. In the first round, we want to know where the array is stored, because actually there's some randomization. And in the second round, based on the result, we calculate the index to our arbitrary location. Now, blocking together, we leak the random seed by erasing, and then forge the control block with the UID XORed with the seed in itself, and then delete the UID and redirect the kernel function pointer. And then we invoke this syscall and enjoy kernel code execution. Now we can't stay too long in kernel mode because there's a watchdog that will catch you. So instead we install a syscall bridge to that RPC interface. All right, we have exploited the MIPS kernel, and the next step is to explore the RPC server. The RPC server looks similarly like that. It sleeps and waits for a request, and if there's some request, it wakes up and fetches the command and the arguments and translates them to native address if necessary, then handles the request and writes back the cache, and finally returns the result back to the client. Now, there are dozens of commands and subcommands, and I wrote a dump fuzzer which would pass random arguments and random commands with random buffers, and it was not sophisticated, because the only feedback it got was whether it crashed or not. But interestingly, it was able to find a lot of null pointer dereferences. So it means that this code hasn't been sufficiently reviewed. I blacklisted some of the uninteresting commands, and then I found a really promising crash. And for reference, the Kermit here is because it's only named the protocol Kermit, and it suits really well because it's for the bug. And the bug is right here. It's a trivial buffer overflow where buff size is too large, is not validated and can be too large. And the probability that the fuzzer was able to find this crash was near 50%. Now the crash happened because of the stack protection, and the stack cookie didn't match. And that's something we need to find out for successful exploitation. Now, common way to bypass the stack protection is to use some uninitialized memory read vulnerability on the stack. But unfortunately, I was not able to find such a thing. And it seemed like Sony made sure to memset every single buffer that got returned to the client. So instead, I had to look for some other bug classes instead, like out-of-bounds reads. And one of the null pointer dereferences was quite interesting. It's in the media engine color space conversion command. And what it does is it gets a YCBCR buffer and converts it into a RGBA buffer. And these pointers come from user memory, from PSP user memory, and they get translated to native address. Now we have these mem copies here because the components are differently sized, and there's some adjustment needed. And they copied the content into a temporary buffer, which is allocated at a constant address. And the bug in this code is that the row is not validated. And it is a 30-bit integer, and as such, we can arbitrarily control the source pointer. Now, we have an arbitrary read, but the content is written to that temporary buffer, and then CSC is applied on that buffer. And that's the formula of CSC. I don't really understand it, but what is obvious is that we lose information due to floating point imprecision or 8-bit truncation. So what if we can set CP and CR to 128? Then the rest of the terms would cancel out, and we would be left with RGB equal to Y. But still, we can't just point to an arbitrary address and expect to control the values there, because the YCBCR buffers are stored consecutively. And it took me a bit of creativity, and I made the observation that that frame buffer was allocated at a constant address, and that the frame buffer was not cleared after the conversion. So that's how we exploit it. We filled the CBCR frame buffer with the value hex 80. This can be done by just calling the command without abusing anything. And then we copy the content of our arbitrary source into the Y component. And we do that by choosing a size such that only a third of the buffer is filled. Now we have the constellation where the Y component contains the information we want to disclose, and the rest contains x80, sorry. Now we want to apply CSC on that buffer, but we don't want to change the content of it. How can we achieve that? By choosing the same address for the source as the destination. And as such, memcopy will not have any effects. And we can then apply CSC, and it will gracefully output the Y component to us. And the last step is to read every fourth byte of the output. Why every fourth byte? Because RGB is equal to Y, so it's the same information. Now, what is it all about again? We had a stack smash, and we wanted to find out the stack cookie, and now we have it. Well, we have obtained an arbitrary read primitive, and we still need to find out that value. The stack cookie is stored in a data segment of some module, but where is that data segment? Remember, there's ASLR, and it can be anywhere. And we definitely don't want to read somewhere and hit an invalid page and make the application crash. Fortunately, there's an easy approach. The PSP firmware is 12 megabytes big and is stored in the PSP data segment. And it's always allocated at these two addresses, which means that there's only an entropy of 5 bits. And it also means that we can read at that address safely, because in the first case, it's 1 megabytes within the segment. In the second, it's only slightly after the start. And from that point on, we iterate backwards and search for some unique constant. Once we find that, we can determine the ASR slide, and from that point on, we can determine all bases and know the exact location of the stack cookie. Now we can put it together. We put the stack cookie at the right position and overflow the buffer and get that exception. We can control PC arbitrarily. And that's always something cool to see, that cool value here. All right. We are now able to execute ROP chains with system privileges, but we want to stay in the MIPS world and orchestrate ARM function calls instead, because we don't want to write complex ROP chains. So for every function call in ARM world, we prepare a small ROP chain that contains that function and the arguments, and we smash the stack with it. And then the ROP chain will restore the context and resume the execution. And then the return value will be returned back to the client. And for pointers, we can just use the PSP RAM and map it to the native address space. But we need to be careful with the MIPS cache. So before we send the command, we need to write back the cache such that the ARM processor can see the real contents. And we also need to invalidate it such that we can see the changes that were made from the ARM processor. And finally, we are able to write hybrid code which use native API, but run on the MIPS processor. Now, we have already attacked the ARM userland, and the last step is to attack the ARM kernel. While developing, I noticed something weird. After multiple ARM function calls, wireless LAN would stop working. How was that possible? We only escaped the emulator, and we didn't touch the kernel yet. It turned out that the buffer we used to smash the stack was passed to a wireless LAN IO control command, and this command would notice that the buffer was not valid and bail out. But while bailing out, it forgot to free some heap allocation. And in the wireless LAN driver, there are only 8 slots available for heap allocations. So that means that after 8 function calls, you would already run out of memory. With the same mindset as before, if there's such a bug, it means that there's potential for more severe bugs. And I found a heap overflow just right after looking at it. It looks like that. So it allocates a temporary buffer and copies user data into it. And then it allocates a work buffer and copies the data from temporary buffer into it with a size choosable by us. And then it frees the allocations in last in, first out order. And this overflow is on a custom heap. Now, why do we even have a custom heap? Because the network stack is based on NetBSD 4.0, and the PS Vita doesn't really have malloc and free in kernel, so that's why they had to implement their own custom malloc-free API. So the custom heap implements a best fit algorithm, which is good for performance, which is memory efficient, but bad for performance. The heap maintains a free list as well as a busy list, and free chunks are always coalesced. So that means that no 2 free chunks can be consecutive in memory. And the heap contains heap cookies, which indicate whether a chunk is free or whether it is busy. And it also contains a heap cookie at the end of every chunk to prevent buffer overflows. But because these cookies are constant, and because we control the buffer of the overflow, we can just simply fake it. And the last step, last but not least, the heap grows backwards from high to low, which is beneficial for us, as you can see later. Now we have a diagram which shows the initial state where we allocate the temporary buffer on the bottom and the work buffer on the top. And the busy head points to the work buffer. And now data from the temporary buffer will be copied into the work buffer and overflow into temporary buffer itself. And because we know what we overflow, like we know what chunks there is, we know that we only corrupt the chunk header. And that's something we need to restore after exploitation. Now, after the overflow, we plant two fake chunks, where the first is a busy chunk, and the second is a fake free chunk. And they point to arbitrary addresses. Now, why does the chunk on the bottom need to be free? Because when freeing, the physical next chunk is considered as free if it is different from the logical next chunk. So if we free the chunk on the top, it will look at the pointer and it sees that the logical next is same as the physical next. In that case, it needs to repeat the procedure. And in the second round, the logical next chunk points to an arbitrary address which is not equal to the physical next. That means that the chunk on the bottom must be free. And that's exactly what happens when we free the chunk on the top. And the busy head also changes. And the fake free chunk now points back to the work buffer. And what do we have above? We have the work pointer written to arbitrary next. And that's our write primitive. Now, we are not finished. We still need to free the temporary buffer. And after freeing that, the busy list head changed again, and now we destroyed the whole data structure. Null is also written to arbitrary ref, and now we have 3 chunks left ready to be merged. After merging the first 2 chunks, we have this constellation, so nothing really interesting happened, but we still have 2 chunks left to be merged. And once again, we have a write primitive where the work pointer is written to arbitrary pref. Overall, we have 3 writes. The work pointer is written to arp top, null is written to arp right, and again work is written to arp bottom. And let's use that to redirect a kernel pointer. This code is used to allocate the hex 800 bytes work buffer. Now, we want to override the value of v4 plus hex 580. Why? Because by doing that, and by executing that code, we can dereference the kernel pointer from the work buffer, which we control. But for that, we need to know where v4 is. So we need a new information leak. So now with system privileges, I was looking for syscalls that were only accessible with system privileges. And I found that one. It's a simple bug where hex 40 bytes are allocated on the stack, but only 8 bytes are initialized. And the whole buffer is returned back to userland. And to exploit it, we just call some interesting syscalls before, and then invoke that syscall to leak the content. All right, we can use that primitive to leak text pointers, or leak the kernel stack base, and most importantly, we can leak the value of v4. Now, with that information, we prepare a kernel rob chain, which we plant in the kernel stack, and we prepare a small stub to pivot the stack. This stub is stored in the work buffer. Now we launch the unlink attack and redirect the v4 plus hex 580 value to the stub. And we can invoke the victim code and kick off our kernel rob chain. That's it. After exploitation, we allocate a read-write page. We copy our payload into the page, and we mark it as read and executable, and then we execute it. In the payload, we restore the heap data structure, and remove signature checks and load the custom firmware framework. And that's it. That was the whole journey from MIPS userland to ARM kernel. Sorry. Now, I want to showcase you the exploit chain. All right, so that's a customized PS Vita, which a friend of mine made. So we now have the Trinity application, which is a PSP application, and now we run it. And we have a cool animation. And now we will get into the bootstrap called construct. It's a reference to Matrix. And now we have the ability to launch homebrews. For example, VitaShell, which is a file manager that I created. And welcome, BlueHat. Now I want to show you some other things that I made. For example, Adrenaline. So as mentioned before, there's a MIPS processor. It can only play PSP games. And I extended it and loaded the whole firmware into it, such that we have a 2-in-1 device. And if you had the PSP, you would recognize it. And the last thing I want to show is Enso. It's a bootloader hack by T-Molecule. And it allows you to hack the PS Vita at the earliest stage. And now we reboot the device. And have a custom logo from T-Molecule. And we boot into custom firmware directly. All right, back to the slides. So, achieved kernel code execution in the MIPS processor by exploiting a type confusion vulnerability and by a race condition vulnerability. And we escaped the PSP emulator by reading arbitrary memory, using color space conversion, and by smashing the stack. And finally, we escalated to ARM kernel privileges using a kernel stack info leak and a heap unlink attack. The source code and a more detailed write-up is available at that link. Please check it out if you want to see how all these things were implemented. And in my final words, I want to encourage you to join the scene. There are a lot of cool challenges. So as mentioned before, the network stack is based on NetBSD 4.0, which is quite old. So maybe you can search for some bugs that have been fixed between 4.0 and the current version and apply them to the PS Vita. For example, a bug I found in NetBSD, I originally discovered on the PS Vita, and then I realized it was still available in the current version. If you're into reverse engineering, you can try to find vulnerabilities in the boot ROM or bootloader, or you can try to reverse engineer driver and port them to Linux, which is work in progress. And myself, I have been working on a save state feature, which allows you to make a snapshot at any point and later restore it, which is technically really fun. And I would like to express my gratitude towards T-Molecule for their prior research. Without them, I wouldn't be able to do all this stuff. I want to thank QuickRacer for the MIPS kernel vulnerabilities. I want to thank my manager and my team for encouraging me and for supporting me. Thanks to Apache and Liblor for slides ideas and for their friendship. And thanks to my family for everything. And Thank you for your attention.